Hello everyone, welcome to Electronics Prepper, a channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I thought I would show you a small and simple circuit that we can use to generate square wave signal of about 1 megahertz, give or take, with pretty sharp edges. Both rise time and fall time are pretty short. I will need this in order to make some experiments with some transistors, and I will want to see their switching ability. I will post a video soon about that. But now I want to show you the circuit because, well, in order to test how well a transistor switches, you need to have a square wave with as short rise times and fall times as possible. And in order to build that, I had some LM6172 in integrated circuits lying around. These are dual operational amplifiers, as we are being told in the datasheet. They're not super cheap, but they're not very expensive either. They're around, I don't know, $8, $10, something like that. So we can still easily buy 2 or 3 pieces just to test some things, you know, to make some experiments. These are 100 megahertz operational amplifiers that have a pretty high slew rate, 3000 volts per microsecond, as we see here. That's quite a lot, and it's more than other amplifiers that have a 100 megahertz bandwidth have. The slew rate, for those who don't know, the slew rate is the ability of an operational amplifier to change its output voltage. It's basically a measure of how fast can the output of an operational amplifier change. Okay, this is why we have the measurement unit volts per second, or multiples and submultiples of that. In this case, volts per microsecond. Okay, so basically I created this circuit, which is pretty simple. It uses both op-amps from this integrated circuit. Both of them are comparators, and my idea was to create the simplest form of an oscillator as possible. What's the simplest form? Well, I don't think it can be anything easier and simpler than charging and discharging a capacitor and monitoring its voltage, basically. So this is what we are having here. I'm powering this from a 15 volt power supply, because I want my output signal to be 10 volts peak to peak or more. So this is what we're having here. We're having this capacitor that's connected to the inverting input of the first op-amp. Basically, this op-amp monitors the voltage on the capacitor. We have a voltage divider here with R1 and R5 that's connected to the non-inverting input of the op-amp, and this basically sets a reference point. And also we have R4, a resistor that charges and discharges this capacitor that's connected straight to the output of the op-amp. The idea is that when we power on this circuit for the first time, this capacitor is of course discharged, and because it's discharged, the voltage across it is 0, So the capacitor, so basically, this op-amp will have the voltage on the positive input higher than the voltage on the negative input, so it will drive its it will pull its output high as possible. This op-amp is not a rail-to-rail op-amp, but it can still get to about 1.5 volts near the power rails. So 1.5 volts less than the positive rail is the maximum voltage that it can have on its output, and 1.5 volts is the smallest voltage that it can have on its output. So when its output will be dragged up high, it will basically provide current through R4 for this capacitor, which will start to charge, and it will charge up until the voltage on the voltage across it will be bigger, slightly bigger than the voltage provided by this divider R1, R5. This basically gives about 5/6 of the whole supply voltage. So in our case, that's 47 divided by 57 times 15. So we have about 12.3 volts of reference voltage here on the plus input. When the voltage on the capacitor slightly goes above these 12.3 volts, the whole op-amp will flip, because the voltage on the negative input will be higher than the voltage on the positive input, so the output will be dragged down to the smallest voltage possible. That's when the capacitor will start to discharge through R4 and the op-amp, but the reference voltage will also change, because when the output will be dragged down to about 1.5 volts, since the output is connected with this diode, this rectifying diode, to the positive input, it will drag down this point, this positive input. R5 will be almost as if it doesn't exist, and so the reference voltage will suddenly drop from 12.3 volts to only about 2 volts. So the capacitor will have time to discharge from 12 point something volts all the way down to 2 volts, when the whole process will repeat itself, you know. And I'm using the second op-amp from this IC to basically compare this voltage and give a better square wave on its output. I have here R2 and R6 of equal value. Therefore, I'm comparing the output of the first op-amp with half the power supply voltage, and this way the output is it's cleaner, because the output of the first op-amp is not so clean due to the capacitor being charged and discharged. In order to better see this, I have also created the circuit in microcap, and we are going to simulate it. And yeah, this is exactly what we are seeing. With red we have the voltage on the capacitor, which we see that it charges up to some 12.5 volts approximately, and then discharges to some 2.1 volts, and then charges again and discharges again. With blue we have the output of the first op-amp, which we see that it's not quite as nice square wave, because it needs to charge and discharge this capacitor. And with green we have the output of the second op-amp, which is also the output of the entire circuit. And we see that in the simulations the square wave is pretty much perfect. It seems to be flawless. In this simulation, the frequency is slightly bigger than 1 megahertz. In practice, what I achieved is something slightly lower, but it doesn't matter. Also, the duty cycle is not quite 50%, but again, I don't really care all that much. What I care for in my experiments and what I care about this circuit is that it should give as short rise times and fall times as possible. That's really all that I care about this circuit. And the only important thing that I will need in my further experiments. And if we are zooming in a little bit on the output voltage, and we are placing two cursors on it, let me see. Okay, so we see here on the bottom time in seconds, and we have a delta, which means a difference basically of 4.2 nanoseconds fall time. And if we zoom in to see the rise time, we would pretty much get something similar. So let me put the cursors. See, also 4.2 nanoseconds rise time. That's pretty fast, and obviously that's a nice thing because that's exactly what we want. Now, in practice, I've made this circuit on a breadboard. Of course, a breadboard degrades the performance of such circuits that work on such frequencies. I will probably create a circuit, a dedicated circuit for it in the near future. But I'm happy to see that I have pretty nice results on the breadboard as well. I have 919 kilohertz, not quite 1 megahertz, but again, I don't care all that much about the frequency itself. And we see that we have pretty sharp rise and fall times. If we are to measure them, I have zoomed in a little bit, and if we are to take a look at this very steep incline, because we don't care about the period of time when the voltage is slowly rising, we care only about the period of time when the voltage is rising fast. We have two divisions of 20 nanoseconds. We see here as well, because I've put some cursors. We have a 40 nanosecond rise time. Same thing for the fall time, it's also about 40 nanoseconds. Yes, it is 10 times worse than the simulated values, but again, it's a circuit on a breadboard working at 1 megahertz. It's obviously not gonna perform all that well. All in all, I'm happy with these results. So I will create the circuit. I'm pretty confident that these times will shorten, will become smaller, and so I will have an even smaller rise times and fall times, so even steeper inclines, which is nice. And yeah, for this particular purpose, I am pleased. So I can definitely recommend this circuit because it's simple, it's relatively cheap. I mean, excluding the LM6172, which is about $8 or $10. You know, basically all the rest are just a few resistors, a diode, and a capacitor, which are pretty much nothing. They're almost for free. So this can be created cheaply, easily. Also, you can use any other opamp that has a very high slew rate, because honestly, this is the only thing that we care about when we are trying to generate a square wave like this with an opamp. All we care about is the slew rate from the opamp. Again, For this opamp, we see the slew rate on the very first page, but also it is written below at some page, page 4 in this case. We see slew rate 3000 volts per microsecond at these conditions, 2500 at these conditions. So this is the thing that you need to take care of, that you need to look at when you decide to use a different op-amp. So I hope you found this useful. Thanks a lot for watching. Don't forget to hit the like and subscribe buttons if you want to see more. Also, if you feel like supporting my work in helping you understand electronics better and helping you build stuff easier, please consider supporting my work on Patreon. The faster I can buy components and devices, the faster I can learn things, and faster I will come here on YouTube and show you as well, so that you don't have to do this same work again for yourself. Thanks a lot for watching. I'll see you in the next video. Bye!